Okay, so we have talked about individual detectors and then their features, right? Now, what is the use of these detectors actually? Why do we need them in nuclear physics? Right now, I'm talking about. Basically, we are interested in understanding the mechanism of the atomic nucleus, right? And how do we do that? We take an atomic nucleus, we excite it. Okay, we excite it, and during the de-excitation, it emits charged particles or gamma rays or whatever. We observe the particles, and then from there we try to infer the excitation state and overall the nature of the nucleus itself. This is what we do. So the question is, life was so good when we are talking about 137 cesium source, single detector, clean spectrum. So why do we need a large number of detectors? Now just think about it. A nucleus level, be a ground state, not just ground state, some excited state. What does it have? Number one, I am talking about an excited state. So excitation energy of the nuclear level. Number one. Number two, angular momentum of the level spin. Number three, parity of the level. Number four, I'm talking about an excited nucleus, it's not stable. So, lifetime of the level. Number four. Okay, four very important things. Now, we can have quadruple moment again of that measurement, all that. I'm talking about four basic things right now. So the question is, how do we know about these things? Normally, you open a book or a research paper, you will see a level spin is given, parity is given, energy excitation is given, the lifetime is given. Have you thought about it? How have people estimated them? How do they know that this is so? The answer to this question is measurements, very different type of measurements. Those measurements will give information about these four basic parameters or properties of the nucleus. Now then again, I am just talking about one particular excited level. There are so many excited levels, right? Very important thing is that in order to understand even one excited level, the four properties of them, we need more than one detector. Just one detector cannot give you information about the features. Just take one example, angular momentum. You need more than one detectors. Understand? So, I am telling you, in a way, a motivation for using more than one detectors, or basically motivation for doing coincidence measurements, right? Now, when we are talking about more than one detectors and we have a large number of detectors, see here, this is an array. We call this a detector array. All are of identical type, these detectors. What are they doing? See, this is a projectile, this hits a target over here, and a compound nucleus is formed from which a residual nuclei is emitted. I am not showing them there, but I am showing the result. The result is say emitted charged particle or gamma ray, whatever. Now, if we want to know about those residual nuclei, their excited levels, we have to detect them. So that's why I have put so many detectors out there. An array is basically large group of detectors, right? But again, they are all of these detectors, they are acting individually, but their result can be correlated together. In software, after the experiment, I can correlate all the detectors. So you can say, just like I have got only 2 arms here, an array can have more than 100 arms. Even though each arm is working individually, but there can be correlation between them. Say for example, look over here. This is a triple coincidence. what is happening? Suppose a nucleus at a time emits in an excite emits 3 gamma rays, and I am detecting 3 gamma rays. Remember, when I am talking about array, I am always talking about the fact that one gamma ray is always detected in one detector. If I am talking about gamma rays itself, right? So don't think that 2 gamma rays are entering one detector. If it so happens, then the detector will detect the energy corresponding to the sum of the 2 gamma rays. It is possible, right? But then the detected energy will be sum of them, not individual. Okay, now, so here I am getting 3 gamma rays from a single nucleus. Now this is correlated event. Why? Because they are emitted from the same nucleus, and given the coincidence window, I can find a correlation between them. There can be 2 coincidence events, even 5 coincidence events, and so on. Let us talk about n detectors. Each of them are kept at the same distance, d. What's the solid angle? Here I have shown, we have already discussed about it. So, source to detector distance is d, detector radius is r, identical detector. So, this is the solid angle. Good. Now, the absolute full energetic efficiency of a single detector, let me denote it as P. This is equal to the solid angle multiplied by the intrinsic efficiency. Okay. So, omega into epsilon. So now let me write down the total efficiency of this entire detector system or the entire array. Now as I have told you, this array is capable of detecting not just singles, not just doubles, not just triples, but even more, right? So we have to consider each of them, right? Contributions together. So the total efficiency is single, doubles, triples. Here triples example I have shown you. So what's the single efficiency? See the number of possibilities, NP1 into the efficiency, full energetic efficiency of a single detector, NP1 into P1, P to the power 1. Next, number of double. Now you might say, sir, why is this different? I will come to this later on. Right now, NP2 into P square, NP3 into P cube, and so on and so forth. See, NPK into PK basically is the efficiency for K-fold coincidence. So you see, this total efficiency depends on each of the terms. You can see. So overall, the number of terms. What does it depend on? Total number of detectors. So it depends on N and also the individual photopic efficiency.
স্যার এখানে এই যে NP3 আছে বা NP1 এগুলো হচ্ছে মানে কতগুলো মানে একটা ডিটেক্টরে একটা কমারে হওয়ার প্রবাবিলিটি কত?
নাম্বার অফ ডাবলস, নাম্বার অফ ট্রিপলস,
সেগুলো আবার কত নাম্বারের ডিটেক্টরে ঢুকছে?
Yes. So last day we have discussed about detector arrays and we have obtained a very simple expression for detector total efficiency, right? Now let us try to understand this using basic examples. So suppose let us consider n equal to 3. So we will be having only 3 detectors. ठीक है सर? n equal to 3. So this is detector 1, or don't call it 1. Whatever you can say. If you want to say 1, then 1. This is 2, and this is detector 3. So they are comprising an array. The source is here somewhere, and so the gamma rays are falling here, 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 and like that. So 3 detectors. Good. So what's the single possibility? Singles detection 1, 2, 3. So singles only 3. Okay. Next, doubles. Now you see, doubles, we have got this possibility. So doubles 1, 2, 2, 3,
3 1.
3, 1. So how many?
3.
3. But actually it is not 3, it is 6.
6.
Why? So 1, 2, then 2, 1, again 2, 3, 3, 2, and likewise. So can you tell me why there are 6 possibilities instead of 3? Try to understand. Okay, let us take an example. Suppose in this reaction, suppose 2 gamma rays are emitted. One is 200 keV and another is 1200 keV. Okay, 2 gamma rays. Let us name them gamma A and gamma B. Okay, 2 gamma rays, gamma A and gamma B. Good. Now let us consider this situation. 1, 2. Detector 1, 2. Okay. And then again detector 2, 1. This configuration, let us try to understand. 1, 2 and 2, 1. Okay, so suppose in the first case 1, 2, the 200 kV gamma ray falls in 1 and the 1200 in detector 2. Next, what is
Reverse.
2, 1?
2,
2, 1.
reverse.
Reverse. But in reverse, does it really mean that gammas will be reversed?
এনার্জিটা রিভার্স মানে
Try to understand. What is the meaning of detector 1, 2? So suppose gamma A in detector 1. Okay, gamma A in detector 1 and gamma B in detector 2. This is meaning of detector 1, 2, let me say. So 1, 2, coincidence. Now the same thing, if it is reversed, how will it look like? 2, 1. 2, 1. Now what does 2, 1 means? Gamma A in detector 1 or detector 2?
স্যার ডিটেক্টরের পজিশন দুটো চেঞ্জ হয়ে যাচ্ছে
So you, okay, you see this is just redundant, this is just the same old thing. So this is wrong. Now, so what is the difference between two? They both seem identical in this case, right? So whether gamma A falls on detector 2 or detector 1, this should not matter because they are identical detectors. Remember, this is what I have said. Now, in reality, two things you must keep in mind. Two things. Number one, in a detector array, sometimes depending on the situation, we use different detectors. Okay, so it is possible. So this is possibility number one. In detector array, the detectors itself are different. So this can be a HBG array and this can be a sodium iodide array. You must be wondering, sir, why are we using a sodium iodide array? It doesn't have good energy resolution, but it has got much better efficiency. So there can be a situation where I need both efficiency as well as energy resolution. In that case, I do a compromise and put both detectors in my array. So in this case, these two detectors are intrinsically different. That's why I have to consider this possibility, right? Gamma A in detector 2, it will be very different from these two situations will be different in that case. The second possibility is that yes, I am saying the second possibility is suppose all the three detectors are HPG. Then you will say, sir, that they are identical detectors. Then why do we consider the scenario? Why do we consider 6 combinations? The reason is, even if I say that these detectors are identical, even if the manufacturer makes identical detectors, remember it is not the detector itself, detector plus preamplifier plus amplifier, all that electronics. Because of this, even though they are made by the same manufacturer, same time production, everything remains the same, their response will be different. This is very important, you must keep this in mind. So, never assume that they will give identical response. And we have experimentally seen that. Say for example, the energy resolution will be slightly different. In one detector at 1 MeV, energy resolution will be 2.1 kV. In other detector, it can be 1.9 kV. They are different. Better energy resolution means, even though they have the same efficiency, better energy resolution means narrower peak, or the peak height will be larger. So, signal changes. Keep this in mind. So, the two possibilities. Number one, detectors intrinsically are different. In that case, we have to consider different possibility. Number two, even if the detectors are identical, then again we have to consider different combinations. Okay. So that's why, that's the reason for using permutation here. 1, 2, 2, 1, and not combination, just 1. So I will ask this in examination. This is important. Physics is involved here. Okay. Okay, so let us now consider again the total efficiency. Remember that we have talked about last time. So this is proportional to both P as well as total number of detectors N. Now let us first consider this P. Now P is equal to the solid angle into intrinsic efficiency. Right. Now you remember, so I have to increase P. So I can increase omega as well as I can increase intrinsic efficiency. The intrinsic efficiency can be increased by having bigger crystals. More crystals, so gamma rays, whatever possibility, they can be absorbed. They will not escape. But bigger crystals mean, remember we are talking about cases where after the reaction, the residual nuclei will fly with a velocity and then it will emit gamma rays. So, bigger crystals mean more Doppler broadening, right? Although bigger crystal is a very costly affair as well, and also this is important, bigger crystals, they are very much prone to neutron damage. This is a very important point. So, bigger crystals, they are very costly, they are prone to neutron damage, and also bigger crystals mean very large Doppler broadening. So, we have to do some compromise. Next, solid angle. Now, we have seen the expression for solid angle. Remember, effectively, solid angle depends on the distance. If we put the source very close, this is the source, this is the detector. If you put the detector very close, then the solid angle becomes large, right? But the detector opening angle again very much increases. So, I can increase the solid angle by decreasing the distance, but this again increases the Doppler broadening, number one. Again, if I put the detector very close, then more and more counts will enter the detector. And suppose the detector data handling capacity is exceeded. Suppose a detector at a time can handle 6,000 counts per second. Just a number. Now, if I put 12,000 counts, then what will happen? The rest of the 6,000 counts, they will just waste it. This means very large dead time. It's a waste. So this you have to also keep in mind, that just decreasing D doesn't help you, because the data handling capacity of the detector will be exceeded, the Doppler broadening will be exceeded. Another way is, okay, you can do something like that. You can decrease the D by what? You can take care of this data handling capacity by decreasing the current. When the beam is coming, you decrease the current, the intensity, then less number of reactions will be produced. Okay, this is a possibility. Now, then again, if you decrease the D, the detector will come close to the source, but then more number of detectors, there will be less, because there is less space to accommodate the detectors. So this means decreasing the D means less N. But we have seen that this total efficiency is proportional to N. So you see there are so many compromises which has to be done. Now, depending on N, you see one of the ways to increase this N, that is the number of detectors, is what? Is to increase the height of the beam line. What is that? Now this is the real floor of the experiment, where the experiment is happening. And this is the projectile. The projectile is coming, it falls on a target. Suppose the target is kept here. Now, you must be wondering, sir, does this thing happen in air or so? No, it cannot happen in air. Because if it comes, if the projectile comes in air, what will happen is that there are so many atoms, molecules in the air, right? They will just interact with them instead of interacting with the target, and something else will happen, which we do not want. It will be very complicated affair. So we want the beam to reach the target. That's why we are using a vacuum chamber, a small beam pipe, where the beam will go like this, and using vacuum pumps, we put vacuum inside it, okay, and so the beam interacts with very much less particles and falls directly on the target. Now, so if this pipe is very much above the floor, then we can accommodate large number of detectors even below the beam line, that means above the floor, along with putting above as well. You understand? So a very important way of increasing N is to increase the height of the beam line and not on the floor. Next, even though the efficiency can be increased by increasing the number of detectors, we have to keep this in mind that we must put HPG detectors as less number as possible in the front angle. Why? Because during the reaction, the large neutron flux will be there, and the neutrons are predominantly emitted in the forward angles. What is forward angle? So suppose this is the beam, right? And this is more or less the forward angle. So I should put less number of HPG detectors over here. Why? Because there will be large neutron flux here, and they will just damage your detector. Certain detectors are very prone to neutron damage, whereas others are not. So I have to put neutron resistant type of detectors, or detectors which are not easily damaged by the neutrons. Try to understand, a detector costs 5 crore rupees. Okay, suppose a detector with the entire anti-compton shield costs 5 crore rupees. 5 crore. Now you have got 4 such detectors. Will you be risking to put the detector at forward angle? It might happen that after 1 hour of beam, our detector gets damaged. So 5 crore rupees goes to waste. Will you be trying to take the risk? No one will does. Right? And remember, all these detectors, they have a lifetime. Just like us humans, just like most of the radioactive nuclei. So it's not that the detector will forever remain good. Why? Because during operation, some flux it will always get. Remember, keep this in mind. These are real experimental experiences. Most of the time, I have seen charged particle detectors being used for roughly 3 or 4 runs. After that, because of intense damage, basically during radioactive beam experiments, you have to throw away. So 50 lakh rupees goes to waste. But again, so I have to utilize those 50 lakh rupees during 4 or 3 very interesting, very important experiments. So very important experiments has to be chosen. This is how we understand, because money is very important. So this is very important. While doing anything, we have to understand what are the things which can damage our products. So here the product is the detector. The neutron damage you have to be very careful about that. So forward angle detectors, you have to be careful. Next, you see, increasing number of detectors means what? I will show you pictures later on. Means large number of electronics. Even a single detector will have amplifier, then on the timing sector, TFA, CFD, and discriminator and all that stuff. So increasing number of detectors means more and more electronics. So your data acquisition, DAC, should be capable enough to handle so many detectors. So what I want to tell you, increasing an array efficiency depends on these factors, and most of them are contradictory to each other. If you increase something, the other decreases. So you have to take all these considerations into account. Okay. Beam light. This is just the beam light. I will show you picture later on. Okay. Show you a video later on. Okay. What I was talking about is, you see, total efficiency. It was proportional to P, right? Which is equal to solid angle into intrinsic efficiency. Now this stuff is inversely proportional to D. So if I decrease D in one way, by decreasing D, I am increasing the total efficiency. But remember, the problems faced. Number one, decreasing D means less N, less number of detectors. Less N means lower coincidence efficiency. Okay, we cannot have higher fault data in this regard. Again, decreasing D means increase in isolated hit probability. What is this stuff? This is very simple. We have already talked about it. The situation or the scenario is something like this. So see, this is the detector. Okay, this is the detector. This is my source. So from this source, gamma rays can come in any direction. It can fall in this source as well. Now if I put the source very close to the detector, what will happen is that basically this source is, if I zoom in, it is a very big chunk, and inside it there are small nuclei, right? And at a time, suppose one nuclei de-excite by emitting one gamma ray, another nuclei can also de-excite and emit another gamma ray, and so on and so forth. Now, if I put the detector very close to my source, there is a possibility that two gamma rays from two separate nuclei, all within the same source, they will enter the same detector. Now, what about the detector? Will it be able to identify these two gamma rays? No. The detector just remembers that there is a time for which I have to collect the data, collect the signal. And so what will happen is that the detector will just give a signal which is equal to the sum of the energy deposited by these two counts. So if each of the gamma rays have 100 keV, then the detector will show you a signal equal to, corresponding to 200 keV. Now this is isolated hit probability. So if I put the source very close to the detector, the possibility of two gamma rays emitted by two separate nuclei de-exciting within the same source increases. And so we get wrong signal, but you can't do anything about it. If there is segmentation also, then it is possible to identify, but there is nothing over here. So how to get rid of this? Put the detector far away. But if you put it far away, solid angle decreases. Okay, solid angle decreases, but at least I will get genuine data. You understand? I must get genuine data. So these are some interesting issues.